All right. I'll begin with a word of prayer. So, Heavenly Father, we thank you for this day again. I thank you for this class and these students. Just ask you to bless our work today. Help us to glorify you in what we do. And we just thank you again, Lord, for your many blessings, Lord. In your name I pray, Lord Jesus. Amen. So yeah, you guys have till Friday, and then what's done is done, right? So, for the computer project. Now, I guess that begs the question: what time Friday? The answer is start a class. So, at least for the report. I mean, I would like to say after class, but then that begs the question: how are you guys going to get it to me? And then inevitably, I'm going to have some team decide that need to delay till Monday. If we could all agree that, like, 4 o'clock on Friday is a reasonable due date that we can all figure out and not push me to Monday on, I probably could extend it to 4 on Friday. Would that be interesting? Do I have agreement from the other table? I see some nodding. Okay, let's make it 4 on Friday then.
So the report's a physical paper.
Yeah, I do need a printout. I do not need a printout of your MATLAB file. I just you can email that to me. Does that make sense? I mean, I don't have any kind of I don't have any assignment in Canvas or anything to submit it to. You just email it to me. That'll be fine. Excuse me. And if it gives you greater joy to email it from like a Gmail account or something, feel free. I know it gives me greater joy to email anything of any size from a non-school account, in my experience. Anyway, let's see here. So, I introduced the Gram-Schmidt last time, and so just a warning from talking to you guys. You guys are like using orth in the computer project, right? And that does something. It doesn't necessarily do the same thing as the Gram-Schmidt we talked about Wednesday. So one of the things that could mean is it could produce a different orthonormal set than, say, with some website you tried or something, right? But that's not a problem. The computer project doesn't say to find a particular orthonormal set. It says to find an orthonormal set that's produced from Gram-Schmidt of a given set of vectors, right? And I told you I'm not being dogmatic about which Gram-Schmidt. So I would like for you to use the Gram-Schmidt which is easiest and is in MATLAB, which probably means to use orth. So that's going to give you some set of vectors. And it might be different than the set of vectors you got from a website, and that's fine. The matrix that you then construct through the formula I gave you, it's going to be different if you use a different set of vectors. But the kind of answers that we can expect from that point forward, like the ABCD part, they're all going to be kind of the same, because I have engineered the matrix to have particular properties, so I kind of know what to expect in your answers. And so if you have those, then you're doing things right, and if you don't, well, then something went wrong. Anyway, so just want to say that. So let's talk about orthogonal complements today. And hopefully the QR decomposition. And so we've talked about LU decomposition for a matrix, right? Well, this is yet another matrix factoring scheme. But this one is based on orthonormality. So first of all, let me just make a definition here. Definition. For S, a subset of Rn, we define S perp to be equal to, excuse me, X in Rn such that, oh man, that's bad. S dot X is equal to 0 for all S. Well, for each, let's say for each, I'll just say for S in S. Oh, fun. All right, so here, for example, we could have S is the single vector 1, 2, 3. All right. Then S perp, the perp to S is, in this context, X in R3 such that 1, 2, 3 dot the X vector equals to 0, right? Sorry. Well, not sorry, I can't stop. But anyway, so what is that? If I break this out, it's x1 plus 2x2 plus 3x3 is equal to 0, right? What's that? I mean, that's a plane, right? That's the plane with normal 1, 2, 3. So the perp to the vector 1, 2, 3 is the plane, right? Theorem. If W is equal to the span of S, then W perp is equal to S perp. In other words, it doesn't matter. Let's see here, say it a different way. If you want to find the perp to a space, it suffices to find the perpendicular to like a generating set for the space. That's nice because let's think about this. So let's discuss this. If we have S is equal to, let's say, S1, S2, Sk, right? Subset of Rn. Then X, an element of S perp, what's that mean? What conditions does that require of us? Yeah. Boy. She loud today. Let's see here. Or maybe I'm just easily distracted. So we have dot products that have to be true for this vector x, right? We have S1 dot x, right? S2 dot x, and so forth. Sk dot x. These are all equal to what? 0, right? But how can we express the dot product? Do you guys remember? So like v dot x is equal to v transpose x, right? So I can erase these dots. I don't even have to erase them. I mean, the point of this is, can you rewrite that as a single matrix equation? What is this? This is the matrix S1 transpose, S2 transpose, Sk transpose times the x vector, equal to 0, right? That's equivalent to the stack of k equations is that one matrix equation. Can you guys tell me what that matrix I just wrote is? So this is the same as, well, what did we've talked about the matrix of the basis, right? So using that same notation here, we have the matrix of S what? It's not the matrix of S because we got all these transposes, right? So it's the matrix of S transposed, yeah? Times X. Equal to 0, right? So what does this say about X? X is an element of what? What's that equation? S transpose times x equal to 0. Do we have a name for this kind of equation? Is this a standard calculation for us? I mean, it is, right? This is the null space. X is an element of the null space of the transpose of the matrix formed by concatenating the vectors in S. So there you go. That is a very straightforward thing to calculate. See, we can calculate the perp to a given set by simply calculating the null space of the transpose of the matrix of the vectors which define the set. Let's put this into practice for our example 1. So if I want to find the perp, so for example 1 continued, my so my S was just the set containing 1, 2, 3, right? Which of course, properly understood, is a column vector. And so in this case, S transpose is just the row vector. What's the null space? X is an element of the null space. Sorry, this example is so dumb, it's hard to appreciate. But X is an element of the null space, if and only if what? X1 plus 2x2 plus 3x3 is equal to 0. All right? So can you find me a basis for the null space? What would be a basis for the null space? In other words, what's a basis for the perp to S here? That's equivalent to the question, what's a basis for the null space? There's no row reduction here to do, right? So it's kind of dumb. I just look at this as x is equal to minus 2x3 minus, minus x2 rather, minus 2x2 minus 3x3, comma x2, comma x3, right? So x solves this, right? Therefore that. So what's the basis for the perp? Well, let's factor the x2 out. We got x2 minus 2, 1, 0 plus x3 times minus 3, 0, 1. Excuse me. Goodness gracious. So it looks like we can use these as a basis for perp, right? We can call this one V1, call this one V2, all right? Can you guys give me an orthonormal basis for the perp to S? How to orthonormalize V1, V2. So what should we do? We should say maybe we'll just let U1 prime equal to minus 2, 1, 0. We'll let U2 prime equals to minus 3, 0, 1 minus 2, 1, 0 dot minus 3, 0, 1 divided by minus 2, 1, 0 dot minus 2, 1, 0 times minus 2, 1, 0, right? What's that? That is the Gram-Schmidt, right? So U1 prime is minus 2, 1, 0. U2 prime, you guys help me out here. What we got? What's this fraction actually equal to there? We've got what, 6 over, looks like 6 over 5 to me. So 6/5. So we've got minus 3 minus what? 2 times 6 minus 12 over 5. Is it a plus?
2 minus.
Oh, yes, thank you. I'll do that. And then 0. So then how about minus 6 over 5 for the next one? And 1, just 1, right? Let's see here. Let's factor the 5th out. So we got 1/5 times, minus 15 plus 12 is minus 3. I think a minus 3, minus 6, and then 5. Right? Moment of truth. If this is legit, right? One of the things that should be true is the dot product of u2 prime with u1 prime. It better be 0, right? So this dot that is 6 minus a good at 0. All right. So the let's say beta, the basis for S perp would be, looks like to me, 1 over the square root of 5 minus 2, 1, 0. And then ignore the 5th. What's 9 plus 36 plus 25? $70? Is it 70? You guys check me on that. I think I got square root of 70 here. I was thinking 36 plus 9 is 45. 45 plus 25 is 70, I think. Did I do that right?
Yeah.
Okay. So there you go. This is an orthonormal basis for the perp of S, which of course is the plane with normal vector 1, 2, 3. Now what can you do with these things? Right? Well, you can do lots of things. So I'm going to call this here U1, call this one U2, right? Let's see here. What would of course, a basis for S itself, I mean, if I think about the span of S, right, span of S has what? That's the span of, well, it's the span of 1, 2, 3, right? But what's the length of 1, 2, 3? 1 plus 4 plus 9. So 1 over the square root of 14. 1, 2, 3. So this is an orthonormal basis for the line that we're talking about. The normal line to the plane. Are those should be perpendicular. Did that work? Behold, the dot product of this and that, 0. The dot product of this and that is minus 3, minus 12 plus 15, also known as 0. All right. So let me give this thing a name. Let me call this one W. And I'm going to call W perp will be, that you can easily see as a span of beta S perp, all right? So what I wanted to talk about here is these subspaces, W and W perp, are examples of what are called complementary subspaces. So the way this works is if you look at R3, right, R3 is equal to W, direct sum W perp. Now what this means, this plus with a circle, it means that the intersection of the two subspaces is just 0. So that makes these subspaces what are called independent. The perp of a subspace will be independent from the subspace, right? Now there are subspaces which are independent and yet not perpendicular. Like, so for example, an example of that would be something like just in the plane, this could be W1. Maybe this could be W2. So in other words, W1 is like the span of 1, 1. And W2 is like the span of 0, 1. It is true that if you add these two spaces together, you get all of R2. And it's also true that the intersection of these two spaces is 0. So those two things together give us that W1, the direct sum W2, is R2. All right, so that's what this notation means, is that they're independent subspaces. But those, it is not the case. It's not the case, right? The W1, W1 is not equal to W2 perp, right? What's the perp of W2 here? If W2 is the y-axis, what's the perp of the y-axis? The x-axis, right. Okay, so, excuse me. I wanted to show you guys an explicit calculation here that wasn't too hard, and I think this is that. I need to talk a little bit more about the general theory. All right, so the question then is, well, let me just state the theorem. So here's the theorem, the big theorem for us. If let's say W1 is perpendicular to W2. So does this notation make sense to you, like what I'm saying, or do I need to define it? What I mean if W1 is perpendicular to W2 is that the dot product between vectors in those two subspaces is 0 for any vectors. So they're perpendicular subspaces, all right? If this is true and W1 plus W2 is equal to Rn, right? Then Rn is W1 direct sum W2. And what that means for us, that there's a bunch of things that means, all right? But we don't need to listen, this could devolve into a theoretical discussion that's like a week long, all right? The full discussion of independent subspaces is subtle. But we just have two of them here, because that's enough for us. And we have some results. Then for each x in Rn, there exists unique x1 and x, well, let's say x and y. X in, oh, that's a bad choice. better not use x again. We just used it, right? So let's, how about other letters? How about y and z? I don't know, you pick your letters you like here. Goodness gracious, I'll choose eventually. Fine, x1 and x2. x1 in w1 and x2 in w2 such that x is equal to x1 plus x2. So if the vectors are, if the subspaces are perpendicular, then each vector in Rn can be split into one vector which is in the one subspace and another vector which is in the other subspace, and uniquely so. Also, the length of x squared is equal to the length of x1 squared plus the length of x2 squared. Why is this true? This is true because x1 and x2 are perpendicular. Remember we proved this theorem about the Pythagorean identity for perpendicular vectors earlier in the course? If like a dot b is equal to 0, then the length of a plus b squared is the length of a squared plus the length of b squared. That applies here. So this is super nice. Like the length of the vector is equal to the sum of the squares of the lengths of these guys. And these guys have names too. So let me let me put it out here. So we say that the projection onto the W1 space of x is equal to x1, and the projection onto the W2 space of x is equal to x2. They're sometimes called orthogonal projections because there's an orthogonality that's driving this whole construction. What are formulas for the projections? Let's talk about it. So if we have a basis, all right, if we have a basis, better yet, not just any basis, what kind of basis do we want? Let's let beta 1 equal to, let's say v1, v2, vk, and beta 2 equal to, for lack of imagination, w1. I guess I could use u's. What do you guys want, u's or w's? Are you going to make me choose? Dang it. Fine. I already wrote w, so w it is. w1, w2. How many do we got here? If this has got k, I'm saying that the beta 1 is a basis for w, and beta 2 is a basis for w2. So apparently there has to be n minus k here, because the other part of this theorem, which I haven't written down yet, is that if you take the union of these two bases, it gives you a basis for all of our n. But anyway, so let beta 1 and beta 2 be orthonormal bases. Orthonormal bases for W1 and W2 respective. All right. Then x is equal to, what is it equal to? Well, it's equal to a sum I equals 1 to k of x dot vi times vi plus a sum, let's say j equals 1 to n minus k of x dot wj times wj. And what are both of those formulas doing? So remember, we learned for like an orthonormal basis, taking dot product selects components, right? So we're just using that idea here. But this gives me the part of the vector which is in W1, and this gives me the part of the vector which is in W2. Simply that. So those are formulas for the projections. Those are formulas for the projections. Excuse me. So this is straight up the formula for the projection onto W1 of x. And this right here is the formula for the projection onto W2 of x. All right. The thing is, you guys know how to find orthonormal bases now, right? So if I give you a pair of subspaces, you can put this into practice. You can find the bases. You can implement these formulas, right? There's more. You can also define orth. So like, what do you think the orth with respect to W1 acting on x would be equal to? So the orth of W1, this should be the part of the x vector which is perpendicular to W1. What is that? In this notation right here, orth of x with respect to W1 is simply x2. But to be more precise, x2 is equal to what? It's equal to x minus x1, which is in particular equal to x minus the projection onto W1 of x. So you see these are natural extensions of the construction of projection and orthogonal projection for a single vector that we talked about in Calculus 3, if you had my Calculus 3. And if you didn't, I still talked about it last class. So there's that. Okay. And likewise, orth for W2, just you put an x1 here, subtract x2, this changes it to 2. All right? Okay. Now, it turns out that there's a super sneaky, extra special way to rewrite those projection formulas in terms of a matrix. Let's see if we can figure it out together. Maybe I will resist the temptation to make it explicit for this because these numbers are horrible. Excuse me. All right. Oh, goodness gracious. Sometimes it is just better to do something abstractly as opposed to try to flesh it out for a numerical example. Because trying to flesh it out for the numerical 1, 2, 3 example I did today, we'll just get lost in the weeds. I know it. So let's try it more symbolically. Let's look at the formula here. The formula we have for the projection, let's focus on the projection to x1. So projection to W1 of x, what was the formula? We had the formula what? Sum I equals 1 to k. What was it?
X dot vi.
Okay.
Times vi.
Times vi. I mean, that's it, right? Okay, so there's a way of rewriting this as a matrix. But this is not something that's in my notes, so this is kind of new for me. I was reading it in lay yesterday, but I'm not sure I remember it. So let me cheat. So the formula I'm talking about here is in like section, maybe in the Gram-Schmidt process, maybe not. Where was this thing? I have kind of mixed feelings about the formula I'm trying to derive right now. Like sometimes I just think it's better to do the dot product like I've written. But what I'm trying to discover at the moment is theorem 10 on page 399 of lay. So, all right, so he has it in terms of a vector y and u1 through up, but my u1 through up is analogous to, his u1 through up is analogous to my v1 through vk. And he found it helpful to write this out. So let's see if that does it for us. So sometimes doing something like this will be helpful. Let's see, does that shake anything loose for us? He also wants to look at the matrix U. He lets the U matrix be, it's basically the basis matrix. It's the basis matrix for 1. So in our current notation, it's like V1, V2, VK. All right. Oh. Eh? Well, yeah. I mean, we can rewrite this as like V1 transpose X, V1 plus V2 transpose X, V2, VK transpose X, VK. And then I think he claims that this is just equal to U transpose U times X. Wait a minute, no, other way around. U transpose times X. Let's see if that makes sense. So what would that be? This would be, so we've got U times, what's U transpose times X? Goodness gracious. So that is like, oh, yowzers, out of energy here. Well, this is a column vector, right? And what are the components in the column vector? They're like V1 transpose X, V2 transpose X, VK transpose X, like that. Oh, goodness. I'm sorry, guys. I think it's, well, this apparently is an identity. It's not, I can't, it's not, what's the word? I can't explain to you why that calculation is holding, but I think it's something obvious. Like in retrospect, I'm going to look at this and go, you idiot. But this is the cost of me teaching at A15 in part. So, but just stupid, obvious matrix multiplication stuff here, I think. So let me just put us out of our suffering and just say that is a step to go from here to here. Let's try to put it into practice, though. Like, let's look at what this looks like. Okay, so like, let me actually flesh this out for a specific case, so we can better appreciate what's being said here. So let's make it really simple. Something like we'll let W1 be the span of, well, we'll keep this three-dimensional. So let's do like 0, 1, 0, and 0, 0, 1. Okay, so W1 is two-dimensional. This is my like, I'll use V1 and this is my V2. All right. So my matrix U, and again in Lay he uses U1 and U2 here, around page 399. So the U matrix, excuse me, is 0, 1, 0, 0, 0, 1. All right. And great. So what's U transpose? Well, that's just this, right? 0, 1, 0, 0, 0, 1. What happens when we calculate U transpose? What do we get? We've got a 3 by 2 times a 2 by 3. So we're going to get a 3 by 3 matrix, right? What's our 3 by 3 matrix look like here? 0, 0, 0, and then 0, 1, 0, and then 0, 0, 1, right? So allegedly, the projection onto this W1 space of a vector x is supposedly given by this UU transpose times x matrix, which in this instance is 0, 0, 0, 0, 1, 0, 0, 0, 1, times my x, which we could say x1, x2, x3. Sorry for Sorry for the unfortunate conflation with the x1 and x2 there are vectors. They're not components, yeah? So I'm sorry about that. I only got so many letters to work with here. So hopefully the context makes this clear that x1 and x2 and x3 are numbers. Whereas x1 and x2 on the rightmost board were vector components of an abstract vector in Rn. There's different usage there. So this gives us 0, x2, x3, right? That is the projection of a vector in 3 dimensions onto this. What is this geometrically? Can you guys tell me the name of this thing? This is the YZ plane, right? It's the YZ plane. So this is a pretty cool trick, right? If we have an orthonormal basis, we can take the matrix of the basis times the transpose. It will give us a what's called projection matrix. So this is called a projection matrix. Why is that? Because it projects onto the subspace, I mean, all right? What happens if you square that? What's UU transpose squared? If I take a vector and I project it onto the subspace, right? And then I take that projection and I project it onto the subspace, what happens? Nothing more, right? It's just where it was. So like this is equal to itself. It's equal to its square. You can easily check that, right? Square that matrix, you get back to the matrix again. That's geometrically obvious because if you take the projection and you project the projection, you go nowhere. So now, let me draw, excuse me, an abstract picture of what's going on here. Oh, actually, let me not do that. We'll do that next time. So the abstract picture that we need, so next time when we talk about this more, we'll need that abstract picture because this sum of the distances formula is going to become like super important for the application of this. Goodness gracious, to the least squares problem. But let me explain to you guys the QR factorization here. It actually is not bad. So QR decomposition. Now this has some terms and conditions here. So if we're given a n, let's see here, m by n matrix. It doesn't have to be square though. An m by n matrix, but this is key. Linearly independent columns. All right, given an m by n matrix with linearly independent columns, you can factor it there exists Q and R such that A is equal to QR. And here's the deal. This Q is, excuse me, orthonormal or orthogonal matrix. Orthogonal matrix. And this R is upper triangular. It's a little bit more than that, but so the Q is actually an m by n matrix. Oh, my bad. I shouldn't say it's an orthogonal matrix. That was too much. I went too far. It's not an orthogonal matrix. That is not true. That is not true. I mean, if A was square, it probably would be orthogonal. But if A is not square, all we can say about this Q is that is a m by n matrix with orthonormal columns. All right. And the R is an this one's upper triangular n by n. So that makes sense, right? M by n times n by n gives us m by n. How do you find the Q? So here's the way it goes. If we have A, let's say, is equal to A1, A2, dot, 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 AN, all right? These are linearly independent. What can we do with them? If you have a linearly independent set of column vectors, you can Gram-Schmidt it, right? So Gram-Schmidt, and we'll get U1, U2, UN, right? But then, like, goodness gracious, A sub I, or let's say J, A sub J is equal to a sum I equals 1 to n of A sub J dot UI times UI. See, because the Gram-Schmidt process gives us an orthonormal basis for the column space of A. And so every column vector can be written as a linear combination of that orthonormal basis. And calculating components with respect to orthonormal basis is as simple as taking dot products. All right. So then what? Oh man. Oy. Sorry guys. I'm just going to stop here because nothing good was going to come in the next 2 minutes. So I'll try to make you guys a video with an actual example of QR here later today. My apologies.